Alright, greetings to everyone. Okay, so let's say we have a problem which says air in a balloon is heated underneath by a set of gunners and the balloon starts to rise. First question says explain why heating the air causes the balloon to rise. Second question says with a volume of 7.4 by 10⁴ meter cube, calculate the energy supplied to the by the gunners to heat the air from 20 degrees Celsius to 35 degrees Celsius. Average density of air is given as 1.2 kilogram per meter cube. Specific heat capacity of air equals 1010 joules per kilogram per Kelvin. Okay, so the first question says that if a balloon is actually being heated, okay, the balloon begins to rise. So they are asking us to know why is the balloon rising when the air molecules inside the balloon is actually heated. Now here is the check. If the air molecules in the balloon is heated, what happens is that the atoms or the element that makes up the air, that the molecules that makes up the air, gains heat. So once they gain heat, they become very agitated. As a result, they start moving in what different positions. That's moving in zigzag manner inside the balloon. Now, when this happens, they actually gain energy. As they gain energy to move higher. Now, the hot fluid or the hot air, as it gains energy, it becomes less dense. That is to say that the density of the air inside of the balloon becomes very minimal, becomes very small. So once the density of this balloon, of the air in the balloon becomes small, what happens? The hot air begins to float up. It begins to float up. So it causes colder air around the hot air to drop down. So the hot air begins to move up. If the hot air begins to move up, and this hot air is actually found inside the balloon actually starts moving up. So it's just a matter of density, simply mass all over volume. Once the hot air gains heat or gains heat, once the hot air or the air actually gains heat, it becomes hot and then becomes less dense. So the density becomes smaller. If the density becomes smaller, it starts moving upwards. When it starts moving upwards, the air, the balloon that covers the air also start moving upwards. So that's actually what happens when heaters actually, when gunner supplies heat to a balloon and the balloon starts moving up. Alright, so let's look at the second part of the question. Second part of the question says, if we are given a volume is given as, okay, if we are given volume V to be equal to 7.4 by 10 to the power of 4 meter cube, okay, this is the volume, and they say the gunner heats, okay, the air from 20 degrees to 35 degrees Celsius. So initial temperature, okay, is, let's use T1 is given as 20 degrees Celsius. So always convert your temperature to Kelvin by adding 273. So you have 20 plus 273 in Kelvin. So that means initial temperature T1 is equal to 293 Kelvin. Okay, final temperature, let's call it C2. Okay, so the gunner heats the air from 20 degrees to 35 degrees Celsius. So final temperature is actually 35 degrees Celsius. So we have 35 degrees Celsius. So as usual, add 273 to it to convert to Kelvin. So that means that the final temperature is equal to 35 plus 273. That's 308. That's 308 Kelvin. Okay. So those are the initial and final conditions of the temperature. Now we are given density of balloon to be 1.20. So density was also given to us, which is rho is equal to 1.20 kilograms per meter cube. We are also given specific heat capacity of air. So specific heat capacity of the fluid, working fluid, which is air. Specific heat capacity. So So we usually use C to represent specific capacity, and it's given as 1010 joules per kilograms per Kelvin. Okay, so we have this. Question says you should calculate the energy supplied by the burner. So energy is unknown, and that's actually heat supply. The energy simply means the heat supplied by the burner, and heat supplied is actually, let's Q stands for heat supply, which is the energy, is actually mass of the air times specific heat capacity of the air times change in temperature of the air. That's how you find your energy. Okay, so the mass times the specific heat capacity times the change in temperature. So first of all, we'll find the change in temperature. And change in temperature, delta T, is simply the final temperature T2 minus the initial temperature T1. So we are going to have a change in C. Change in temperature is simply final temperature was given as 308 Kelvin. So we have 308 minus initial temperature was given as 293. Okay, Kelvin. So that simply implies that the change in temperature is equal to 308 minus 293. 50. So that's 50 Kelvin. So the change in temperature is actually 15 Kelvin. So if change in temperature is 15 Kelvin, we'll be able to, from the energy equation, we've got change in temperature. We were also given specific heat capacity of the air. Was given to us as this 101 joule per kilogram per Kelvin. So all we need to obtain now is the mass. We don't know the mass of the air. So we need to find the mass of the air. Now recall that we are given density of air. Density of air was given to us as 1.20. So recall that density, which is rho, is actually mass all over volume. Okay, so this is actually mass over volume. So we are given volume from the equation. Volume was given to us as 7.4 by 10 to the power 4. So all we need to do now is to make the mass subject of the formula. If we make mass subject of the formula, we are going to have a mass of air, which is N, which is simply density times volume. Okay, so that simply implies that the mass of air is density. Density was given to us as 1.2. So 1.20 times volume is given as 7.4 by 10 to the power of 4. So this means that the mass of the air will be equal to simply 1.2 by 7.4.
88820. 0 and 2 places.
Okay. 0 kilograms. So this happens to be the mass of the air. So if this is the mass of the air, it becomes easier for us to calculate the value of the energy supply. So the energy supply, therefore, is Q equals to, say, is N, specific capacity times change in temperature. So energy is simply the mass is 88800 times the specific capacity was given to us as 1010. So we have 1010 by change in temperature. We obtain change in temperature as 15 Kelvin, so by 15. Therefore, energy is equal to this multiplied by
134532.
134532.
000.
That's all. 1345.
110.
Yes.
134532
One more zero.
Yes.
Okay. So in joules. This is energy supplied to the air or to the balloon by the voice. So the continuation of the equation says, the C part says, the first balloon used was filled with hydrogen and sealed to keep the volume constant. Okay, so as as the balloon rose, there will be change in pressure of the hydrogen due to the temperature changes of the atmosphere. First question says, calculate the new pressure exerted by the hydrogen if the temperature changed from 20 degrees Celsius to minus 5 degrees Celsius in the balloon. Okay, as the balloon moves from ground level. Okay, so the pressure exerted by the hydrogen in the balloon at ground level is given as 1.01 by 10 to the 5 Pascal. The second part of the question says, state two assumptions that she carried out. Okay, so first thing you need to understand is that they said that the first balloon used was filled with hydrogen and sealed to keep the volume constant. So that is the first thing you need to pay attention to. It was sealed to keep the volume constant. So volume is constant. Let's bring that now our parameters. We have that temperature changes. Temperature moves now from 20 degrees Celsius to minus 5 degrees Celsius. So initial temperature becomes initial temperature, which is T1, is equal to 20 degrees Celsius, and it's actually 20 plus 273. Always convert to Kelvin. So that gives us that T1 is actually 293 Kelvin. Now the final temperature was given as T2 is now equal to minus 5 degrees Celsius. So take note of the change. It goes from 20 degrees Celsius to minus 5 degrees Celsius. So there's a change in temperature. And of course, always add minus 5 plus 273. So it means now that the final temperature T2 is actually 268 Kelvin. So this becomes the initial and the final temperature. Now we are asked to find the new pressure, which is because the pressure at ground level was given. If the pressure at ground level is given as 1.01 by 10 to the 5 Pascal. So initial pressure, which is pressure at ground level, the initial pressure, that's P1, pressure at ground level was given as 1.01 by 10 to the power of 5 Pascal. The question is asking us to find the new pressure, which is final pressure. Okay, final pressure, which is P2, actually unknown. Now remember, we said the volume is kept constant. If the volume is kept constant, it means initial volume and final volume are the same. So initial volume is equal to final volume. So the volume is actually kept constant. So this actually means that V1 is equal to V2. Alright, so we are now going to apply equation of state for an ideal gas. For an ideal gas, the equation of state simply is V1 all over T1 equal to P2 V2 all over T2. That's the equation of state for an ideal gas. And since V1 is equal to V2, that volume is constant, it means this equation will now be transformed as P1 V1 over T1 equal to, in place of P2 now, okay, P2, in place of V2 now, since V1 is equal to V2, so it means I can write in place of V2, I can simply call it V1 all over T1. So notice that these volumes can actually cancel out because they are now the same, the volumes are the same, they are constant. So that simply means that we have P1 over T1 equals P2 over T2. Now, initial pressure was given, initial temperature was given. The new pressure is what we're looking for, which is final pressure, that's P2. The final temperature was also given T2. So we make P2 subject of the formula. If we make the final pressure, which is P2 subject, we are simply going to have send this man or cross multiply this man over to the side. So I'll have T2 all over T1 times P1. So T2 comes that becomes T2 times P1 all over T1. So the final pressure is actually T2 times P1 over T1. Okay, so this is now important. T2 is the final condition of the temperature, which gave us 268. So we have 268 by P1, the initial condition of the pressure, which was given to us the pressure at ground state, which was given to us as the initial pressure 1.01 by 10 to the power of 5. So we have 1.01 by 10 to the power of 5 all over T1 is the initial state of the temperature, which was given to us as 293 Kelvin. Okay, so you have that as 293. So it means the new pressure is actually 268 by 1.01 exponential 5.
2706800.
000.
Yes.
4 over 293.
9238.252.
92382.
Yes.
Point
0.25.
let's keep it going. Newtons or pascals. So that is the value for the new pressure. Okay, asserted by the binding. That's the value for the new pressure. Okay, at constant volume. Alright, so the next question is state two assumptions that you carry out. The first is that volume was kept as constant. So if volume is kept as constant, it means that initial volume is equal to final volume. That's the first condition or assumption carried out. Then the next assumption carried out is by applying the ideal gas equation. Which is that P1 by T1 equals P2 V2 over T2, which is invariably the equation of state for an ideal gas. Alright guys.